In level 2, we will be evaluating exponential functions and solving exponential equations. The exponential equations will always be written in a certain way where we can write the equations where the two sides have the same base. So they're just certain exponential equations. This shows up on the ACT. Kind of easier exponential equations than what we're going to see later on in this unit. Okay, so that's kind of the big focus of level 2. So starting with this first example, we already have the same base on both sides, and that's what we want. We want the same base raised to some exponent. If you ever have an exponential equation where the bases are the same, for the equation to be true, the exponents have to equal each other. So once you have the same base, all you have to do is take your exponents and set them equal to each other, and that's your new equation that you're going to solve. And this is just a simple linear equation. I subtract 4 from both sides, and we get x equals 4, and that's my answer. The reason this works, if I plug in 2 for x, I get, 4 for x, I get 2 to the 4 plus 4, or 2 to the 8th equals 2 to the 8th, which would have to be true. Okay, so for part B, we don't have the same base, but we could rewrite these to have the same base. 27 and 9 are both 3 to some power. 27 is 3 to the 3rd, and 9 is 3 squared, which is then raised to the x plus 1. So I'm going to simplify this right side a little more. I leave the left side 3 to the 3rd. Since I have a power raised to another power, I need to multiply those powers, and I'm going to have to distribute that 2 to both the x and the 1. And I get 3 to the 2x plus 2. So now I have this equation where both of my bases are the same, so I can just set the exponent parts equal to each other. So my new equation that I get is 3 equals 2x plus 2. So I just took those exponents, set them equal to each other. And I subtract 2 from both sides, and I get 1 equals 2x. Divide both sides by 2, and we get x equals 1/2. And that would be my answer. Now in this next one, really similar, 8 and 32 can both be written as 2 to some power. 8 is 2 to the 3rd, which is then raised to the x plus 4. 32 is 2 to the 5th, which is then raised to the x. Then I multiply my powers, so that 3 is going to be distributed to the x plus 4, and I get 2 to the 3x plus 12 on the left side. And on the right side, I multiply the 5 and the x, and I get 2 to the 5x. Now I take those exponents and set them equal to each other. And my new equation is 3x plus 12 equals 5x. So I would subtract 3x from both sides, and we get 12 equals 2x. Divide both sides by 2, and x equals 6. Here are a few more examples that get a little bit harder and apply a few more properties of exponents. Looking at this first one, I already have everything with the same base, but I need to combine my terms on the left side. So if you multiply two expressions with the same base, the rule is that you add the exponents. So if I'm going to multiply 6 to the x squared times 6 to the 5x, I can combine those by adding the exponents, and I get 6 to the x squared plus 5x. And then on the other side, I'm just going to leave it 6 to the 14th. And now that I have one base on each side, I can set the exponents equal to each other. So we get x squared plus 5x equals 14. And now I would need to get all my terms to one side, so I can solve this quadratic equation. I subtract 14 from both sides and set it equal to 0, and then I solve by factoring, and this one's going to have two solutions. So I need two numbers that multiply to negative 14 and add to 5. I get plus 7 minus 2, and so x would be negative 7 or positive 2. In this next example, the base that I would probably like to use is 3. The left side already has 3 to some power, so I'm not going to do anything to the left side. On the right side, 1 over 27 is like 1 over 3 to the third. And I can move 3 to the third up to the top and make that a negative exponent. So that's actually 3 to the negative 3. So I'm going to replace 1 over 27 with 3 to the negative 3. And now I have my two bases that are the same, and I can set the exponents equal to each other. X plus 2 equals negative 3. Subtract 2 from both sides, and x equals negative 5. Okay, and one last example. For a 128, these numbers can all be 2 to some power. So I'm going to rewrite everything as 2 to some power. And we get 2 squared to the x squared on the top. 8 is 2 to the third to the x plus 2. 128 is 2 to the 7th. So this is 1 over 2 to the 7th. I'm going to multiply my powers right here, and we get 2 to the 2x squared. On the bottom, I multiply the powers, and remember to distribute that 3 to the x and the 2, and I get 2 to the 3x plus 6. And then I can rewrite 1 over 2 to the 7th as 2 to the negative 7th. And then on my left side, since I have two expressions with the same base that are being divided, the rule is that I can subtract the exponents. So I get 2 to the 2x squared minus this expression down here, which needs to be in parentheses, 3x plus 6, equals 2 to the negative 7. I can simplify and distribute that negative on the left side, so I get 2 to the 2x squared minus 3x minus 6 equals 2 to the negative 7. And now I can set my exponent parts equal to each other. So we get 2x squared minus 3x minus 6 equals negative 7. This is a quadratic equation, so I need to add the 7 to both sides. So I have 0 on one side, and I can solve by factoring. And we get plus 1 right there. So I factor this. I need a 2x and an x to multiply to 2x squared. The only things that multiply to 1 are 1 and 1. I need this to add to negative 3x, so I want a negative 1x and a negative 2x, which means these both have to be negative. And then my answers are going to be the numbers that make each part equal to 0. 2x minus 1 equals 0. Add 1 to both sides, and we get 2x equals 1. Divide by 2, and x equals 1/2 is one solution. And then x equals positive 1 would make the other part equal to 0.